Hi everyone, so in the previous video we talked about Kirchhoff's first rule, where we talk about junction rule where the algebraic sum of current into any junction is 0. Now let's move on to Kirchhoff's second rule, which is also known as the loop rule. So loop rule says that the algebraic sum, so again it's the sum of something, but this time it's not sum of current, it's the sum of potential difference in any loop, including those associated with EMF and those of resistive elements, must equal 0. Okay, so this time it's a sum of something, but it's not sum of current, it's sum of potential difference. Okay, so this is sum of V is equals to 0, but this one valid at where? In any loop. Okay, so this one is valid at any loop. Okay, so here I'm going to pop up a simple circuit in order to help me explain the idea of loop rule over here. Okay, so this is a circuit that we have studied actually from the potential divider video, where we have 6 volt of power supply or source of EMF, and this source of EMF here will provide energy for the resistor over here. So there's a 1 ohm resistor and a 2 ohm resistor, and based on the potential divider video, we learned that this 6 volt over here will be divided across this 1 ohm and 2 ohm resistor. Because 1 ohm resistor is less in terms of resistance, it will receive less energy, that's why its voltage is less, compared to the 2 ohm resistor, which has a greater resistance, therefore it will have a greater voltage across it. So this is a this is a circuit that we have went through before, but I'm going to use back this circuit to explain the idea of loop rule. Okay, so loop rule says that we are going to sum out the potential differences, but these potential differences can be due to EMF, and it can be due to resistive element. So EMF is the source of EMF over here, so this one has a certain voltage to it, and the resistive elements represented by these two resistors over here, also they will have some voltage across it. So you can see there's 6 volt, there's 2 volts and 4 volts over here, and we need to do an algebraic sum of these potential difference, and we are supposed to get back to 0 for a closed loop. But you can see that if you take 6 plus 2 plus 4, you get something like 12, which doesn't really make sense. So here I'm going to tell you how does a loop rule, how you should understand the idea of loop rule actually. Okay, so here I'm going to set up by introducing a voltmeter over here. The voltmeter will have one leg connected on this side of the circuit over here, and the second leg over here will be connected to different points along the circuit, and we are going to study the voltage at across 2 different points in the circuit. So let's say for the first part, I'm going to connect my leg at this point over here, which is fixed. But for the second leg over here, I'm going to first connect it using this purple line to this point over here. So you can ignore the red, green and blue line and just focus on this one leg, followed by the voltmeter connected to this point over here. So this is actually just measuring the potential difference across the battery, or you can say the potential difference across the EMF only. So in this case, if you find it, I believe your answer you should be 6 volt, right? So the answer that you should obtain over here should be 6 volt. Okay, but today if you choose to shift this purple leg over here, instead of putting it at this point, I'm going to shift it further down the loop. Remember, this is a loop. Okay, so let's say today I'm following my direction of current. My current is flowing in the direction outside the battery, is from the positive terminal to the negative terminal, right? So outside the battery, I'm saying outside the battery, so this is the direction of current. So let's say today I'm following this direction of current, I'm shifting my voltmeter leg, shifting down this current path until I get past the 1 ohm resistor. So now I'm referring to this red leg over here. If my leg on the right leg is still fixed at this point, but let's say my left leg is being shifted to this point over here. So from our understanding of a charge point of view, the charge will receive 6 joule of energy from the battery because it goes from the low potential terminal to the high potential terminal. So it will experience a gain in energy, right? So if it experience a gain in energy, there will be a 6 volt potential difference, a positive 6 volt potential difference over here. But once it get past the resistor over here, we know that resistor, it requires energy to pass through, right? So that 6 volt over here will decrease because some amount of energy is allocated to the resistor. Okay, maybe it's easier to think about it from a 1 coulomb charge perspective. If you think about 1 coulomb charge perspective, for 1 coulomb to pass through this battery over here, every 1 coulomb will receive 6 joule of energy from the battery. That's the idea of 6 volt. 6 volt is 6 joule per coulomb. Every coulomb will receive 6 joule energy from the battery. So coming out from the battery, that 1 coulomb of charge will possess an energy of 6 joule, and you carry that 6 joule until the moment where it starts to enter the resistance. Okay, because the resistor requires some energy to pass through, the charge, the 1 coulomb charge, which initially has 6 joule energy, will lose 2 joule energy in order to be provided to the resistor over here. So when it comes out from the resistor, it will end up with only 4 joule of energy left. So you gain 6 joule from the battery, you lose 2 joule to the resistor over here. So that's why you think about it, the net outcome will be, you come up with 4 joule of energy. So in thinking about it in terms of per coulomb of charge, now we can say that in terms of voltage, we can say that for this red path over here, you initially have a gain of plus 6, but now you have lose 2 due to the resistor, then you end up with only 4 volt. That's what you can see. Okay, then now if you continue on your journey over here, where you move along the current path past the 2 ohm resistor, then now the similar thing will happen. Just now you initially lose 2 joule energy, coming out with 4 joule energy, but now you have 4 joule energy, you pass through this resistor, giving out all 4 joule energy to the 2 ohm resistor. So you come out from this 2 ohm resistor with 0 energy left. Okay, a charge receives 1 coulomb charge receives 6 joule from the battery, lose 2 joule to the 1 ohm resistor, and lose the remaining 4 joule, lose 2 joule to the 1 ohm resistor, and follow up by losing 4 joule to the 2 ohm resistor. 4 joule is the remaining energy left lah, so that all 4 joule will be given to the 2 ohm resistor, resulting in you coming out with 0 joule energy. Okay, so if you connect your voltmeter using the green path to this point over here, you should see that what happens right now is that you have an initial gain of 6, but you lose 2 joule to the 1 ohm resistor, then you lose another 4 joule to the 2 ohm resistor. So at this point, you see that you have 0 volt left. Okay, so this is how you can see how we actually sum out the potential difference due to the battery together with the resistance. And when we when we continue the journey down the current path until the end, going back to the same point, you see this blue path over here. This blue path over here is actually the same as the green path actually. Why the blue path is the same as the green path? Because you can see that green path, if we shift it to the blue path, you are not going through any circuit component. There's no EMF from here to here. There's no resistive elements from here to here. So the green path is essentially the same as the blue path. So you can see that when we go back to the initial point, when you close out the full loop already, you see that the potential difference, if you sum them all up, it will all be equals to 0. So this is actually sum of V equals to 0 volt. Okay, you have gone through a complete loop already, a complete closed loop. So throughout the closed loop, you have seen some gain in potential difference. Okay, and at some point you see some loss in potential difference, and at the end when you come back to the starting point of the loop, you see that if you sum them all up, the amount of potential gain will be the same as the amount of potential loss. So you see that this sum up everything, you get back to 0 volt. Okay, so that's the idea of Kirchhoff's second rule actually. Okay, if we go through a complete full loop, you see that if you sum up the gain and the loss of potential, you get back to 0 as well. Okay, so if you think about it, actually makes sense, right? Because potential, this voltmeter here is measuring the electric potential difference between the one leg and another leg. If you take the potential difference between this purple leg and this black leg, we see that the potential difference is this 6 minus 0, that's why you get 6. Okay, if you check the difference in potential between the black leg and the red leg, then it will be 4 minus 0. If you check it for the black leg and the green leg, then the point over here will be 0. The black point over here will be 0. So 0 minus 0. Okay, so of course, if you come back to the same point, you are taking the same point minus the same point. the same point must have only one electric potential. So if you take the electric potential at this point minus the electric potential at this point, you get back 0 because there's no difference between the two values. This point and this point, of course, the potential is the same. So if you find the difference between the black leg and the blue leg, there's no difference at all. So the answer, the sum of it will be equals to 0, or you can say the potential difference will be equals to 0. Okay, so that's Kirchhoff's second rule, but let me unravel it and draw it in the form of graph in order to have a clearer understanding right now. So here I'm opening up this path over here. So I'm going to start from this point and I'm going to follow the current path over here where we will pass through the battery, follow up by the 1 ohm resistor and the 2 ohm resistor until we come back to the same point over here. So let me label the important information over here, where you have 6 volt battery over here, you have a 1 ohm resistor over here, and you have a 2 ohm resistor over here. And now we know that the current path is actually from left to right in this diagram. So this is how the current will flow along this circuit. Okay, so right now I want to study how the potential changes at different points along the path. So here I'm already set up a graph over here, and let's try to study what happened in terms of the change in potential. Okay, so I'm going to go through this journey from left to right. So initially I start with 0 joule energy for every coulomb of charge, but once it passes through the battery, you gain 6 joule energy, right? So if we draw the diagram, we'll see that this will be maybe in purple. Okay, initially you have no gain energy, but once you pass through the battery, you gain energy up to 6 joule per coulomb. Okay, so you can see a rise in potential over here from 0 to 6. Okay, and when you exit the battery, you go along this connecting wire. So along the connecting wire, there will be no potential changes. There's no gain, there's no loss because this is just a wire. But once you pass through this resistor over here, the resistor tell you that you lose 2 joule energy for every coulomb, right? So dropping 2, you'll be falling to 4 over here, falling to 4 volt over here. Okay, so it should be something like this. Okay, then you continue your journey along the wire where there's no potential changes. But once you pass through a 2 ohm resistor, you know you lose another 4 joule energy for every coulomb. So that's why you drop by 4 volt over here. So dropping by 4 volt makes you come back to 0. So this is you coming back to 0. Continue your journey until the end. Okay, so this is how you can see the potential rise and fall throughout the whole closed loop. And you can see the amount of rise over here is equal to the amount of loss over here. Okay, any gain will also accompany by the same amount of loss over here. So if you sum them all up, you see that the initial and the final will get back to the same level. That's why there's no difference between initial and final potential difference if you go through a closed loop. Okay, there's no difference in the electric potential between the initial electric potential and the final electric potential. They will be the same. Okay, if you go through the whole loop, because the amount of gain is the same as the amount of loss. Okay, so after we understand this thing, I would like to discuss about perspective actually. Okay, today I tell you I'm going to follow the current path when I want to go through this whole closed loop over here. So I'm going through from left to right. But that is actually just perspective. I can choose to go through this loop from in an anti-clockwise fashion. Then that will be me going through this diagram from left to right. Okay, so if I choose to go through this diagram from left to right, okay, maybe in orange. Okay, if I choose to go through this diagram from left to right, imagine I'm a charge and I'm going through this diagram from left to right. The kind of perspective, the kind of things that I'm going to see is initially you experience a gain of energy by 6. Then after that, there'll be a loss of energy by 2. Then there'll be a loss of energy by 4. And the answer of all this summing up will be equals to 0. Okay, that still follows the sum of V equals to 0. Okay, where if you sum up all the potential difference associated with EMF, and resistive elements. If you sum them up, you get 0. Okay, but this is just perspective. Today I choose to go through it in the anti-clockwise fashion. I can equally choose to go through it in the clockwise fashion. Means I can go through it in this direction instead. So if I choose to go through this in the opposite direction instead, which is going this path, now the kind of thing I'm going to see is initially when I pass through the resistor, what happens is I experience a gain of 4 joule of energy per coulomb. So that means that if I choose to walk through this loop in an opposite direction, what I'm seeing is the opposite of what I understand. Okay, if I follow the current direction, follow the direction of current, I know that when the charge passes through the resistor, it should give out energy to the resistor. That's why you will lose energy. But today, if I choose to walk through this path in the direction opposite the current, if I'm walking this path in an abnormal way, opposite the current, I'm seeing that when I pass through the resistor, instead of a loss, I'll be seeing opposite of loss, which is a gain. Again, this is just perspective. It's not exactly, it doesn't have to be what actually happened. This is just how I analyze the loop. I can choose to analyze it in a clockwise, anti-clockwise fashion. I can also choose to analyze it in a clockwise fashion. If I analyze it in an anti-clockwise fashion, I'm just following the current path. But if I'm analyzing it in an opposite direction, which is the clockwise path, I'm analyzing it opposite the direction of current. So if I'm analyzing it opposite the direction of current, what I'm seeing is an abnormal thing, where initially, if normally we think that we pass through resistor, we lose energy, but because we are reversing our path, reversing our perspective, it'll be a gain of energy. Okay, continuing on that same idea, when we pass a resistor opposite the direction of current, you also see a gain of energy instead. So this will be +2. Okay, then now when you come to this battery over here, we know that battery is supposed to supply energy, so you're supposed to have an energy gain. But that is if you follow the direction of current going from low to high. But right now, if we are going in this opposite direction from right to left, what we are seeing is we are going from a high potential terminal to the low potential terminal. So if you go from high potential terminal to low potential terminal, technically you have a loss of energy, right? From high to low, you are falling, you're losing potential energy. So that's why you should experience a loss of energy here instead. So it should be -6. But if you sum them all up, it should also be equal to 0. Okay, so what am I trying to prove here is you can choose to analyze the loop in any direction you prefer. You can analyze it in a clockwise direction, in this case, not following the direction of current. You can choose to analyze it in the anti-clockwise direction, following the direction of current. If you are opposing the direction of current, you should expect that passing through resistor, it will behave the opposite way of what we usually know, where usually it's a loss, but opposite it will be a gain. Okay, and if you go in different way passing through the EMF, if you go from low to high, you should expect a gain, but if you go from high to low, you should expect a loss. Okay, so this is just telling you that you can analyze the loop in different perspective. As long as you go through a full loop, you sum all the potential difference up, it should be equal to 0. Okay, so what you can see here, it's actually energy gain is always equals to energy loss. Okay, in a loop, in a closed loop. So based on that idea, we can further go and say that any potential rise, okay, potential rise is the same thing as energy gain. It's just that potential rise is per coulomb. Okay, joule per coulomb is voltage, right? So any potential rise means why you have things like this, potential rise, we have an equal amount of potential drop as well. Okay, so if you take your potential rise minus your potential drop, you should end up with 0. And this is what sum of V is equal to 0 is all about. Okay, if you take potential rise, which is if you go in the right, if you go towards the right, the potential rise is due to the battery, positive. You minus all the potential drop. If you go to the right, the potential drop is due to the resistors. Then if you sum them all up, it will be equal to 0. That's the idea of Kirchhoff's second rule actually. Okay, so now I'm done explaining Kirchhoff's second rule, but I probably need to summarize a bit in the form of table. There's the sign convention that we use, when we use positive, when we use negative, so that it can be easily applied in a question. Okay, so here I'm going to talk about when do you put positive sign, which represent a gain of energy. When you usually put negative sign, which represent a loss of energy. Okay, I'm going to talk about source of EMF. And I'm going to talk about resistive elements. Okay, resistive elements, it can be external resistance, it can be internal resistance also can. Okay, any kind of resistive element. Okay, so for source of EMF, for battery to be simple. Okay. Wow, cannot draw things straight. Okay, so if I'm going through the battery, if I'm analyzing my loop in this direction, you can see that I go from low to high. And that's a gain of energy. So gain of energy, in this case, I'm going to use positive epsilon. Okay, but on the other hand, if today I analyze it in the opposite direction, okay, it's still the same arrangement of battery, but instead of analyzing it from left to right, let's say today I'm analyzing it from right to left. Then right now I'm going from high to low. So going from high to low is a loss of energy. That's why this one should be negative epsilon. Okay. Sorry, can't stand that line not being really straight. Okay, continuing on that, if we talk about resistive element, you have to be aware of where the current is flowing. What direction is current flowing? Okay, so let's say today if we have current flowing, let's say to the left. Why is my hand shivering that much? If you have current flowing to the left. Okay, so right now, if we, and let me draw it from both rows first. If our current is flowing to the left, now if you are analyzing it from left to right, that's an abnormal way of looking at it, right? Because we are looking at it opposite the direction of current flow. Okay, so in this case, abnormally things behave the opposite of what we usually understand. We know that if you pass through a resistor, it will lose energy, your charge will lose energy. So if you analyze it in an opposite way, it will gain energy. So this time you put positive, what this will be positive IR, because we are talking about resistive elements. If they follow Ohm's law, then you can say V is equals IR. So therefore you can write as positive IR. Okay. On the other hand, if you choose to study in the direction following the current, if you're following a current, you're analyzing it in the normal way. So the resistor will behave the way you usually understand the resistor, which is a charge when it passes through a resistor, it will lose energy. Okay, so because you lose energy, you'll be a loss, that's why it will be negative IR. Okay, so this is how you should, the kind of sign convention that you should keep in your mind when you're solving any questions using loop rule later. So if you talk about EMF, you don't need to talk about the current. You just need to see whether you're coming in from the low terminal or high terminal. You're exiting from the high terminal or low terminal. In high, out low, or in low, out high. That determines whether you have a gain or loss. That determines positive or negative for source of EMF. But for resistive elements, you have to see whether you are analyzing it following a direction of current. Normally there'll be a loss, but if you're following opposite the direction of current, which is an abnormal way of looking at it, then things will behave the opposite way, where it will be a gain, then there'll be positive IR. Okay, so later in a few questions, you study how do you use Kirchhoff junction rule and also loop rule to solve any problem involving complicated circuits with combination of series and parallel and multiple batteries. That's it for Kirchhoff rules. Thank you very much.